Okay, so now I'm going to do an example where we compute the work done on a particle as you move it from one point to the other. Let me remind you what I was saying in the previous video. So here's the idea about work. Everything I drew it on the xy plane last time, but you can actually work in space. So imagine that you have some mass in some object at some initial position. You want to take it to some final position, and the idea is that to move it from this point to the other, you have to choose some trajectory. By trajectory, I just mean a curve. So maybe the curve looks like that. Okay, and what we care about is the fact that where you started at some time, which we call initial time, and you bring it to this point at some final time, which we will call t sub f. Okay, and this curve has some equation r of t. And as you move the particle, well, you have to exert some force to move it. So the force that you exert along this curve may vary from point to point in magnitude and direction. And so the idea is that the total work, and this is how in practice we will compute this, what you do, you think of work as the integral, as a time integral of power. So you integrate this from the initial time to the final time of the dot product between f and the velocity of the curve. Okay, and well, what you will see in the next video is that actually, if you had chosen another trajectory, which is not necessarily this one, this number would not necessarily be the same. So what we will say is that work is path dependent. And then it will become a very interesting question to determine for which forces actually you don't need to worry about the trajectory that you choose. But I'll tell you more about that in a couple of videos. So let's do an example so that you see how this is supposed to go. This in practice is very straightforward. The main idea is like the concept behind it, because the calculation is easier than the double and triple integrals you have been working up to this point. So let's just find the work. So in practice, I will be giving you some vector field. Along the curve t squared t cubed for t01. Okay, so again, F, you think of a force field. That means that at each point along the curve, it is changing in principle in magnitude and in size. So this is giving you the formula for the force at the point. Maybe I should have been a little bit more precise. What this is saying is that you're going to draw a vector at the point x, y, z, and the coordinates of this vector that you're drawing are these three. And so this point can actually be on the curve or not, but eventually we would just care about the case where the point actually belongs to the curve. But in principle, the force field, you can still draw it for other points. It's just that we don't care about what's going on here. And this is a particular curve. Remember that the curves are functions of time, so I'm saying that the position vector of the curve is t squared, t cubed for t between 0 and 1. So at time 0, you think of that as like the initial time where you're moving some particle. You start at the origin, and at time 1, you end up at the point 111. So according to the formula, the work, W, would be the integral from 0 to 1, that's the initial time, the final time, of f dot b dt. And so now we just have to work out all the terms inside this integral. Notice that f dot b is a dot product, so this is really like a number. So you're actually integrating a scalar, right? Work is a scalar, so you'll get a number at the end of the day. So f, as I said, is y minus x squared, z minus y squared, x minus c squared, and b is the velocity vector of the curve, that's 1, 2t, 3t squared, and then what we get, we integrate against t. So this ends up becoming, again, do the dot product first, and then you get 1 times this, so it gives you y minus x squared plus 2t z minus y squared plus 3t squared x minus z squared, and this we are integrating against t. Okay? Now you have to look at this expression, and maybe you'll find it a bit funny, because you say, well, okay, you're trying to do the integral with respect to t, so does that mean that y and x are z and y squared and all of these other things, are they constants or are they variables? I mean, they cannot be constants because x, y, and z represent the position of the particle as you're moving it. So the key concept to recall here is that along the curve, x, y, and z become functions of time, right? So along the curve, x is a function of time. Which function of time? Oh, just a function t. Y is a function of time, which is t squared, and z is also a function of time, which is t cubed. So the idea is to replace every instance of x, y, and z with their corresponding functions in terms of time. So really you always get like a function of time when you're doing these integrals. So the work becomes the integral from 0 to 1 of y minus x squared. But again, along the curve, y is t squared, and x squared becomes x, well, x is t, so x squared becomes t squared. Then 2t, now along the curve, z is t cubed, and y is t squared, so y squared is t to the 4. And finally, 3t squared. And then along the curve, x is t. And along the curve, z is t cubed, so c squared is t to the 6. And all of this against dt. So now we do finally get something that should look a lot more similar to things we have done in the past. So we just simplify this a little bit first, so you get like the integral from 0 to 1 of 2t to the 4 minus 2t to the 5 plus 3t cubed minus 3 t to the 8 dt, and that's not too bad to integrate because it's from 0 to 1. So this becomes t to the 5, 2t to the 5 over 5 minus 2t to the 6 over 6 plus 3t to the 4 over 4 minus 3t to the 9 over 9. Again, this at 0 and 1. So you get 2/5 minus 1/3 plus 3/4 minus 1/3 again. Okay, and well, let's just finish simplifying it for fun. So this is, well, let's use common denominator 1560, so 6 to 24 minus 20 minus 40. Right, I mean, I'm counting this already twice, so 2 times 10, so yeah, that's fine. And then plus 3 times 15, so plus 45. And so that gives you 5 plus 24, that's 29 over 60. So the work, again, which is supposed to be a number, in this case just gives you 29 over 60.